here we have to use what is called the chain rule. This looks complicated, and it somewhat is, but in some other sense it's not. So here I have different buttons that let me choose how my f function looks. Here I can choose my g function, and then here you have so my f function is, in this case, right now it's 1 over 10 t squared, right? So it's this parabola here, right? And my g of x is 2 times cosine x plus 2, so it's this function here, right? And what do we do with these two functions? Well, we compose them. What does that mean? It means that we take the output of this function and plug it in as the input of this function, f of g of x. So we get 1 over 10, and then a parenthesis, and then everything that we have here put into that parenthesis squared. This may look complicated, but a lot of functions are in fact built this way. So if you want to think of this in a way where you sort of can distinguish the different layers, think of you as walking maybe just on a straight line. Okay? So x is your position on this straight line. Okay? So g of x is something else. Let's imagine that the x you got from a GPS. So it only tells you where you are, not how high up you are. So your altitude might be this number g of x. So right now our x is here. So at this point we are standing here. Okay? In fact, I want to do this differently. It's easier if we say that the f here is the altitude and x is time. So at time x equals now minus 0.78. At that time we are at this position. Okay, 3 point something. And now we say that f instead is the height. So where are you at this point? Well, we have to find out. We are here, which means that we are at our height is given by this function, so we are now at this height. Okay. So the composition of these two functions gives us this blue function here. First, you say, at what time are we somewhere? Well, at time x. Where are we? We are here. Given this x, we can find a t. T is basically the same as g of x. And this t we then plug into our f, and then we have this position, this height. So if we now vary these, you can see how this looks, right? So imagine we are now at this time we are at this position. Okay, this position has a given height. We can find that by going down here, finding the height, and we are at this height, right? Clearly, if you just look at this function here, we can find any height at any position. But what we might be interested in is what our height is at any time, right? Then we have to compose the two functions. So x is time. Given some time, we get a position. At that position, we are at this height. Okay. Now you all know that walking downstairs is easier than walking upstairs. So if you want to calculate how much you're going up or down, you should find the derivative of what? Of where you are on the map? No. On how steep it is at the point you are. Well, not really, because it depends on how fast you move, right? If you're going in this direction, you're going in the negative direction here, right? This is what this indicates. What does that tell us? Well, we are at this point, height-wise, and here it goes up, right? But we are walking in the negative direction. We're in fact going in this direction. So to see if we're going up or down, we should in fact both use the information that we are going in the negative direction and that the slope at the point we are is positive. So if the slope is positive and we're going in the negative direction, we're going down, right? This is also what we see here. If we want to know the magnitude of how much we're going down, it turns out that we should just multiply the two. So how fast are we going backwards, and how steep is the slope? Okay, then we get the steepness of this. So here you can see this f prime of g of x tells us how steep is the mountains at this point. Okay, this g prime of x tells us which direction are we going. We're going in the negative direction at a certain velocity. And if we multiply these two, we get this slope here. So for example, here we're going rather quickly in the positive direction. And the next question is, where are we? Well, our position was g of x, so we should plug this g of x into our f function. Then we get this. And the slope here is not very big. But having a lot of velocity, big velocity, and a small steepness means that our going up rate is sort of a mix between these two, right? It's the product of these two. We could do something else. We could look at something like this. So what is this? So now our landscape is this f of t, which is sine of t, right? So the landscape is just going up and down at the same pace the whole time. Agree? But what about our speed? Well, our speed, our position. What about our position? Our position is this. So this is this parabola here. So this means that for large negative x, our speed is big, our velocity is very negative, right? But in spite of the fact that we're moving really fast, this tells us that we're moving very fast, right? The slope is big, but we're not really going up or down anywhere. Why is that? Well, it's because we're at that time at the bottom of one of these hills here. Why is that? Well, you can find the g of x here. You can go down, find the corresponding t, and then you can see that we're at the bottom here. So almost 0 times a big thing is almost 0. And if you plot the function, you get this, right? So here you're going fast, here you're going fast, in the middle you're not really going fast. Then you get that you're going up and down a lot, right? And this means that the derivative goes crazy, right? Because you're going faster and faster up and down. right? You can see that the slope of these pieces becomes increasingly large. So that gives us a crazy derivative here. But the take-home message is that to find the derivative of composition of two functions like this, you should just find the slope of the function, the outer function, at the point you are, so to speak, and the speed you're moving at a given point.